Hi, this is going to be the Friday, October 14th lecture since there was the career fair today, which I hope you enjoyed. I'm going to be picking up the lecture from where we left off on Wednesday, where we were talking about conditional probability. And we were wrapping up the class with this example where we have class rank as either freshman, sophomore, or junior, and the frequency of each one of those class ranks, and a total of 89 students. And if you recall, we already went through, well, first of all, the experiment is we're just going to choose 2 students at random without replacement. And then the first question is, well, what's the probability that the first one's a junior and the second's a freshman? So we set up this notation. J sub 1 is the event that the first is a junior and the F sub 2 is the event that the second's a freshman. And then we went through using the frequency table and the definition of the multiplication rule for probability and use that to look at our table. And I just saw an error here. Let me change that to an F. Oh no, that was right. And came up with that there was a 3.7% probability of this event happening. Now we get to the second question related to this example, and that is, what is the probability that one is a sophomore and the other is a junior? Okay, so let's work on this problem now. Here, what we're going to do is we're going to basically define the event E, and it's going to equal, and I'm just going to copy that it's that one is a sophomore, one is a sophomore and the other is a junior. Notice that here it doesn't really matter, that order doesn't matter. So order doesn't matter. Okay, so what we want to do is kind of count how this is possible, how this can happen. And a good way to do this is through something called a tree diagram. So actually, let's go ahead and get a new slide and move this question over. It'd be kind of nice to do this all in one. All right, well, let's go ahead and move it over. And I'll just get the table as here as well so that we can kind of remember what it said. All right. I'm just going to put this over here for now. All right, so let's try and see if we can draw this. Oh. All right. Let's just start out with a little dot here. And then we're going to, I'm going to create a table just to help us kind of space this out correctly. I don't know how much we need here. Let's see. Probably a lot more than this. All right. That's okay. We'll sort it out in a minute. Okay. So, I'm going to do a tree diagram. And so what we're going to start out with is the first student. I'm just going to use the notation that we were using when we answered part A. So we have that the freshman, so the letter F for freshman, sophomore, junior, FSJ, and then 1 if it's the first student chosen. And then we're going to have, if it's a sophomore for the first, student chosen. Or if it's a junior for the first student chosen. Okay, And then to do our tree diagram, what we're going to want to do then for the second student is in this square, we're going to have that the second student is a freshman, or the second student is a sophomore, or the second student is a junior. And we basically are going to copy this over for each one of our choices of whatever happened on the first student. Let me just get rid of this. I don't think I need that column. Maybe I do. Let me add it. Well, we'll come back to it. Okay. So the way this tree diagram works, let me see if I can make it a little bit smaller. It doesn't want to let me. Because we're going to oops. Thank goodness for Control Z. Let me get rid of these rows. I want to delete these rows, and I think I'm going to delete these rows. So we start at some location, and we're just going to go ahead and say, well, one thing that could happen is you could choose a freshman or a sophomore or a junior for your first student. And then each one of those has a 3 choices for the second student of being chosen. I think I can do this a little bit easier. This way. All right, so these are all the possible paths of what could actually happen. And what we want to do is basically determine what is the problem, what is using the relative frequency, what is the probability that each of these things will happen. So we're just going to populate what each one of these branches is. So the first one is going to be the freshman on the first student. So that's 16 divided by 89. I'm going to just shrink this down a little bit here. Okay. And then when we're talking about the sophomore being chosen for the first student, we're going to talk about, we have 55 over 89, just like we were doing, we did part A. And then for the junior being chosen, it's 18 options out of 89. Okay, now we're going to go in and we want to put in the probabilities for each one of these branches. So if we picked a freshman for the first student, for the second student, there's only 15 left. So the probability is going to be 15, and there's only 88 students left. So this will be 88. I'm actually going to do this. So we have 15 out of 88 here. And for the second student, we're going to have, now we've chosen a freshman for the first student, and we want to know what's the probability of choosing a sophomore for the second student. Well, the 88 is right, but now we still have all 55 sitting in the classroom. So that's a 55 divided by 88. And then for the probability of getting a junior for the second student, we're going to see that all 18 are sitting in the room. So this is going to be 18 divided by the 88. Okay, so now that we have these, I'm going to attempt to copy this over. And so we can, let me see if I can do this a different way. You guys are watching me do a bunch of PowerPoint here. All right, so let's slide this down here and we'll modify these numbers. Okay, so the first one is we have a sophomore for the first student. So for the freshman, all 16 are there. So we want to change this to a 16 over 88. For the sophomore as the first student, if we're going to choose a sophomore as the second student, there's now only 54 left in the room. And for the junior, there's still all 18 there. So that's fine. Oops, I only grabbed one of them. And it happens sometimes when you copy stuff. You gotta be careful to grab all. Okay. So now if we pick a junior as the first student, the second one, there's still all 16 freshmen in the room. And there's all 55 sophomores. But now for the juniors, there's one less because we chose one for the first student. So that's 17. All right, so now once we have all the ways we could choose the two students sort of diagrammed out here, what we want to do is identify what are the ones that we're asking about. So what we want to know here is how do we get one that's a sophomore and the other is a junior? So one way that we could do this is we could go this branch. So sophomore followed by a junior. The other way it could happen, right, is if we start out with a junior and then we choose a sophomore. So let's just call the first way we could do this. Let's call this B1. And we'll call the second way for branch one. We just kind of try to want to identify the branches where we have this satisfaction of our event. Okay. All right. So what we could say, right, is that this event E is equal to so let me just write this. So we want to find the branches that satisfy the event. Note, only one of these or the other can happen, right? So B1 and B2 are mutually exclusive. So when we look at the probability of E, we get that this is equal to the probability of B1 or B2. So either one happens, we will have satisfied our event. So the probability of B1 or B2 for mutually exclusive events, if you remember, is just that adding up. There's no overlap. And if you were to draw this as a Venn diagram, when they're mutually exclusive, the probabilities are just the probability of one plus the probability of the other. Right. So now that we've gone this far, what we actually need to go do next is figure out the probabilities for B1 and B2. So by the basic counting rules, or let's kind of keep writing here first of all. So the probability of B1 is going to be that the sophomore is chosen first, right? And the junior is chosen second. And then the probability of B2, we look at down here at B2, it's that the junior is chosen first. Oh, he does this. Probability, let's see how it works now. The junior's chosen first. So it's junior's chosen first. And the sophomore, sorry, is chosen second. So what's that equal to? Well, by the basic counting rules, what we're going to do is multiply the probabilities for each event. So for the first event, what we're going to have is the 55 divided by 89 times the 18 divided by the 88. And then we're going to add to that the 18 divided by 89. And multiply that by the 55 divided by 88. What we get, if we multiply this all together, is 0.253 or 25.3%. So the probability of this happening is that one's a junior, one's a sophomore, is slightly over 25% of the time. The next thing I want to talk about is independence. Let's start out by defining independent events. So event B is independent of event A if probability of B given A is equal to just the probability of B. And so the interpretation of this is that means that the probability of B is not in any way affected by whether or not A happens. It couldn't care less. Note, by definition, if B is independent from A, then A is independent from B. If not independent. Then A and B are what we call dependent events. From this, we're going to get the special multiplication rule. Which just says that for two independent events, I'll start out saying by recall that, so I'm sort of giving it to you and deriving it at the same time. So we want to talk about the probability of A and B. And if you remember, that's the probability of A times the probability of B given A, right? That's how we defined it last class. But now we have the situation where we have independent events. So what that tells us is that the probability of A is the same, but the probability of B given A is just the probability of B. So the thing to notice is that because of the independence, this probability of B over A given A is just going to be the probability of B because it does not care. The other thing to note is this can be extended to more events. So if A, B, C, dot, however many you have are independent events, then the probability of A and B and C and dot is just going to be the product of all of them. So it's the product of A times B times the product of C and a little note, another kind of note is that in probability, A cannot be dependent on B, but B be independent of A. So if it goes one way, it goes both ways. If one is independent from another, the other one's independent from the other. They're just independent from each other. Okay. And then another note is that mutually, I'm going to add this note on the next page. Better save this. So mutually exclusive events versus independence. I didn't mean to make that title that big. So no, mutually exclusive events are dependent. So for example, things that are mutually exclusive. Well, let me just start out with an example. I might help. So consider a coin toss. So events are heads or tails. And they are mutually exclusive. One of the things that's a characteristic of mutually exclusive events, or one of the things that's characteristics of dependent events. So characteristic of dependent events is that the non-occurrence of heads implies the occurrence of tails. It's also a characteristic of the mutually exclusive. Mathematically, we would say that the probability of A, so let's let A, H, how about we set H is heads, T is the event of getting tails. And the probability of probability of H of heads and tails is equal to 0. Okay, so right now we're talking about mutually exclusive. To contrast that kind of with independence. So you can kind of see the difference. These are not independent. And then the other one would be to kind of understand how it's different. Let's consider an example related to coin tossing that's independence. And that would be toss 2 coins. So each one can have heads or tails. So heads or tails, each coin are independent events. Because if you toss a head on the first coin, it doesn't matter what you get on the second coin. So let's go ahead and set that up. Let's say X is equal to heads on the first coin. And Y equals tails on the second coin. And then mathematically, the probability of heads on the first coin and tails on the second coin is given by the probability of X times the probability of Y. next thing I want to talk about are the counting rules. So in here, we're basically thinking about the topic is getting the F or N in the F over N rule. The number of ways something can happen is what we're going to call counting. Let's do an example. Consider characteristics of fellow students. We're going to consider two characteristics. One is what is the color of the car that they own. We're going to consider black, which we're going to abbreviate with a B, white, gray, or, and then we have other / none. And we're going to just give that the letter O. And then we're going to look at their class rank. And again, we're going to look at freshman, sophomore, or junior. And the question is, how many possible combinations exist for a random student? Okay. And so for this, we're going to go back and we're going to select, see if I can grab everything here and try not to grab that. That's not going to work. Okay. We want to do another tree diagram to help figure this out. And let's see if we can select this and erase it, select this and erase it, select this and erase it. Might have been more effort to erase everything than to just start fresh, but the joys of doing stuff on the PowerPoint versus just drawing it on a piece of paper. All right, so we're going to start out by doing the car color. So we want to put all the options here. So we would have black, white, gray, or other. And then instead of freshman, we have freshman, sophomore, junior, but we don't need the little twos afterwards. So this one, we're just going to call it class rank. Now that we've kind of diagrammed out how many of these, all the possible paths, might be good to realize, like if we're trying to count how many of these combinations there are, that in this little group over here, there were 3. So for each possibility for a car color, there are 3 still possibilities for class rank, right? And so it's gonna be a big pain in the butt. Okay, I'm not gonna do that. All right. So basically our options right now are going to be BF, BS, BJ, WF, WS, WJ, GF, GS, GA, or OF, OS, OJ. Okay, so if we want to count up how many of these we have, we would say, well, it's 3 plus 3 plus 3 plus 3. And so that actually is 3 4 times, right? Which is going to be 4 times 3, which is just going to equal 12. And so from this, we're going to get the idea of what we call the basic counting rule. Which says that given M objects, we're going to choose R of them without replacement. And then now choose R objects again. Each unique set of R objects. Oh, this is all wrong. Okay. Which says, suppose that R actions, whoops, I don't want it that bold. Suppose that R actions are to be performed in a definite order. Furthermore, suppose there are M1 possible outcomes for the first action, M2 possible outcomes for the second action, etc. Then altogether, there are M1 times M2, and so on. And multiply them all together, however many there are, up to M, the rth action. And maybe I'll do sub R. Possible outcomes. So multiplying them all together is a basic counting rule. R. Consider the previous example. Where we were talking about characteristics of students. R was equal to 2 for ask, this was the action, ask car color. And the other one was ask class rank. The number of ways which we could have a car color was black, white, gray, or other none. So we kind of gave them a survey sheet, right? Gave everyone a survey sheet. And so there's 4 possibilities there. And the number of ways that we could have a class rank in our class, oops. Sorry, something got messed up. So the number of ways for the second action for class rank was 3, either freshman, sophomore, or junior. And so from here, we saw that the total possible outcomes was equal to, so it was M1 times M2. That for us equaled 4 times 3, or 12. So the next thing I want to talk about, you need to recall the stuff we did at the beginning of class of the semester when we talked about factorials. So recall that k factorial is equal to k times k minus 1 times k minus 2. And you keep taking 1 off until you get to 2 times 1. And we agreed by definition make that 1. We're now going to be talking about permutations. So let's start out by just stating what this is. And I think it becomes pretty clear as we work through it. Given M objects, you're gonna choose R of them without replacement. And now you choose R objects again. Each unique set of R objects where order matters. Is a permutation. And so once we understand what a permutation is, so like let's say you take the letters A, B, C, that is considered a different permutation than CBA. So the order matters even though the objects themselves are being repeated, they're just in a different order. So each ordered combination is a permutation. And the question that we always ask or that we hit once we understand this in probability is we have to count how many there are. So let's start out with an example. We're going to consider four colors. Red, which is going to have R. Oops, not that. What this is R. Green, blue, or yellow. And the experiment is to choose two of them without replacement. Question: how many permutations are possible? Well, here we see that the number of objects, M, equal four, and the number that we're choosing, R, is going to equal 2. So let's do a tree diagram for what this looks like. So here I've started to put together the tree diagram. So let me continue to do that. Okay, so now I have completed the tree diagram of all the possible ways to pick two colors without replacement from the four colors, red, green, blue, and yellow. So the first color is going to be one of the four, red, green, blue, and yellow. The second color is going to be one of the remaining three colors. And if we just read across and down the branches, we can get all the different permutations. So red, green, red, blue, red, yellow, etc. Okay, now that we have that done, let's try and count how many we have. So if we go over here and we want to count how many we have, we see that by the basic counting rules, the number of permutations is going to equal the four options we had for the first one times the options each one of those four had for the second color. So that gives us 4 times 3, which is equal to 12. And for a permutation, the math notation is, stop. It's going to be a something that I don't know if I can get it to look right. in the notation that I'm using here. It's not wanting to do it. So it's a sub 4. So it's the subscript 4, which is the number of objects P permute 2. And this formula is read for permute 2. Or this, the way we would say the number of permutations is 4 permute 2. So here we get to the permutation rule. And this says that the number of possible permutations of R objects from M possibilities is given by this M, subscript M, then a P, then an R. And that formula is M factorial divided by M minus R factorial. So in the previous example, we had that it was 4 permute 2. And what we saw was that we had 12. So let's see how this formula gives us that here. We're going to do the 4 factorial. We're going to divide that by 4 minus 2 factorial. And that's going to equal the 4 factorial divided by 2 factorial, right? And that's just 4 times 3 times 2 factorial divided by 2 factorial. And that's just going to equal the 4 times 3, which is just the 12. So we see that the formula will work, and it will, not only will it work in a small example like we just did, that we can kind of prove it to ourselves it works, it keeps working. Even for large numbers, that would be very tedious to do a tree diagram for. Then the next thing I want to talk to you about is the special permutation rule. And that just says that the number of ways of ordering M objects is M factorial. And we can kind of see the derivation of this just from the permutation rule. So we can just see that if we have m objects and we're going to take all m of them, so that we want to choose m of m things, how many ways can we do that? And it's m factorial divided by m minus m factorial. And then so that's just going to be m factorial divided by 0 factorial. And we agreed that 0 factorial is 1. So it's m factorial divided by 1 or just m factorial. We'll put a box around this permutation rule, because this is one of the ones you're going to want to have in your notes and be familiar with. So the next topic I want to cover is combinations. So this is the, like this, hold on. This is the number of ways of ordering, combination, order does not matter. So back in the previous example, where we were choosing colors, two colors, 4 choices. So here, remember, we had m equals 4 and r equals 2. Let's go back and look at those. Okay, so here are the permutations that we had arrived at before. And when we're going to try and think about what are the combinations, we basically are going to take what's here. So we take red, green, but that is equal to green, red. So the order doesn't matter. So this one we've already taken care of. So then we can go to the next one and get red, blue, but that's equal to blue, red. We're taking care of that one. And then the same thing with each one of these. Red, yellow is equal to yellow, red. So we will have, we can take care of yellow, red already. So these are equivalent when it comes to a combination. So now we can see that the number of combinations is much smaller than the number of permutations. And in fact, the number of combinations that we're seeing here, if we were to count them, is 6, right? And that 6 is actually equal to 12 divided by 2. And you're like, okay, why did you do that? And it's because I'm trying to see how or motivate where the combination rule comes from. And 12 was what the number of permutations are. So I'm trying to see, how do you go from 12 to 6 using the previous rule? So we know that the 12 comes from the m factorial divided by the m minus r factorial. And then this would be, that gives me the 12. So then this would have to be multiplied by half. Let's make this a little bit bigger so we can see it. Okay. So if that's the case, how do we get 2? Well, r was 2. So it turns out it can be shown by many examples or by proof, mathematical proof, which we're going to be skipping over, but that the formula is going to be the m minus r factorial, and then we're going to also divide by r factorial. And we can get the formula for that. So from that, we get the combination rule. It says that the number of possible combinations of R objects from a collection of M possibilities is given by so we have this M choose R. And it's going to equal this M. Let me just copy this formula here so I don't have to retype it. And we say that this is M choose R. And in our previous example, so here we're talking about these combinations. What we actually were dealing with, right, was 4 choose 2. Oh, I was in a math mode, sorry. 4 choose 2. So according to the formula, it should have been 4 factorial divided by 4 minus 2 factorial divided by 2 factorial. And that's just going to be 4 factorial divided by 2 factorial and another 2 factorial. And that's just going to equal 4 times 3 times 2 factorial divided by 2 factorial and another 2 factorial, right? So 2 of the 2 factorials are going to cancel out, and we have 4 times 3 or 12 divided by 2, which is equal to 6. So we see the formula will work. One thing to notice from all this too is that just by the very nature of the way it's set up, you're always going to have that the number of combinations is always going to be less than or equal to the number of permutations, right? And just ignore those little dotted blanks there. It's just an artifact of the math notation software. But if I were to put this in, I believe that maybe if I come back to it, no, it's still there. But I know that if I put it in slideshow mode, you won't see it. Okay, so that's just an observation that we see is true. And then the last thing we want to talk about is the applications of all this counting stuff to samples. So given a population n of size n, and choose a sample of size at little n. Note, when we choose a sample, order does not matter. We're just sampling from a larger population. The number of different samples that you could choose is so it's going to be this choose function, except we're going to start out with capital N and we're choosing a sample size of little n. So big N, choose little n. All right, so let's do an example of this. Sorry. Consider quality assurance TV sets. Department, let's say, at LG or something. So the procedure is to choose 5 TVs at random from every 100. So in this case, we're saying our population, if you will, is going to be 100, and we're going to choose a sample randomly of 5. If the truth if we actually looked at all 100, we'd determine that 6 are defective. What is the probability that 2 of the 5 in the sample will be defective? And why 2? Well, you could say at most 2. So this is what you would do this. You would figure out what's probability that there are 0, what's probability that there's 1, and what's probability that there are 2. But we're just going to do 2. And so you would add up those different probabilities from each one of those situations to get the probability that it's no more than 2. But this is just an example of the building block, if you will, of how you get to that more realistic question. But let's say the question, we're simplifying the question. Instead of being what's the probability that at most 2 will be defective, what we're going to say is what's the probability that exactly 2 will be defective. Okay, so let's set this up. Let's define the event as being 2 of 5 are defective. Right? And we're going to say then that the probability of this event is going to equal, we're going to do the F over N rule. Okay, so the first thing we're going to want to do is we want to get the N. And this is just going to equal the number of possible samples. We already saw that we can get that. Actually, let me just do an equal sign here. Let me see if it's still in my buffer. Good, it is. So we're going to be choosing 5 out of 100. So 100 choose 5. And we're going to, we already saw that this is 100 factorial by the formula, and 100 minus 5 factorial. Oops, I forgot. I have to add the extra parentheses to do this in this math equation editor. 5 factorial. All right, so that's just going to be 100 factorial divided by 95 factorial times 5 factorial. And you can put this in your calculator, or you can, if your calculator blows up, if you try to do this, you may have to simplify it down. If you have to simplify it down, you will see that it's going to be 100 times 99 times 98 times 97 times 96. So tedious. Times 95 factorial. Okay, and then denominator, we have 95 factorial and 5 factorial. Okay. So the 95 factorial and the 95 factorial cancel out, right? So this cancels out with this one. Same thing, top and bottom. And so what we're left with is a number that hopefully will not blow up your calculator. And it comes out to 2,010,660. Oh, sorry, no, I'm looking at the wrong number. 75,287,520. Okay, then the second thing is we have to get the F. So we got the denominator. It's usually a little easier to get the denominator. The numerator is the number of ways that the event can be true. So we want to get F, which equals the number of ways to choose 2 defective TVs. And one of the things that helps when you're trying to put these together is to realize that this also means in 3 not defective TVs. That's really what choosing 2 is saying. It's 2 that are defective and 3 that are not defective. And it's frequently helpful to do a schematic. So I'm going to set up a schematic. Okay, so what we're going to do is think about all the TVs and group them into 2 groups of the 100. Since we know the truth is that there were 6 defective, and then there's 94 that are not defective. And so what we want to actually do here is we want to think about how we choose these. So of the 6, we're going to, 2 have to be chosen out of those 6 that are defective. And in order to get our event to happen, right? Remember, our event is that we choose 2 defective. So even though they're all mixed together, we know that they're 6. So in order to get 2 defective, we had to choose 2 of those 6. And then we also have to choose 3 that are not defective. So the number of ways to do this is we are going to say it's 6 choose 2 for the defective ones and 94 choose 3 for the not defective ones. And now we're just going to do the calculations of what this turns out to be. So by the basic counting rules, the number of ways for this to happen is going to equal this product of each of these, right? So we have the 2 things that need to happen, and we need to know the number of ways each one happens. So this is going to be 6 factorial divided by, I'm just going to go ahead and write 4 factorial. So that's 6 minus 2 factorial times 2 factorial. For the 6 choose 2. And then for the 94 choose 3, we do the same thing again. We have 94 factorial divided by, we're going to do 94 minus 3, so 91 factorial, and 3 factorial. And you can simplify that down, or just if you have a strong calculator, you can, with a little good buffer memory, you should be able to calculate this. This is 2,010,660. So now that we have all this, we are able now to go ahead and answer the question. So we can say, so the probability of E is just going to be F divided by N. So for us, it's just going to be the 2,010,660 divided by the 75,287,520. And that turns out to be 0.027 or 2.7%. So the number of ways that we'll get exactly 2 defective TVs, let me restate that. The probability of getting exactly 2 out of the 5 that we sample as being defective is 2.7% probability. Okay, and that wraps it up for chapter 4.